Chapter 3, Random Variables and Binomial Distributions. If we roll a fair die, the possible outcomes are the numbers 1, 2, 3, 4, 5, and 6. And each of these numbers has probability 1/6. Rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. Rolling a die produces a random variable whose possible values are the numbers 1 through 6, each having a probability of 1/6. Mathematicians and statisticians like to use variables to represent numbers. Uppercase letters are often used to represent random variables. Thus, a statistician might say, let y be the number that comes up on the next roll of the die. So a random variable is a numerical outcome of a probability experiment. It's got to be a number. And random variables can be discrete or continuous. So a random variable y is discrete if it can assume only a finite or countably infinite number of distinct values. Another way of thinking about that is that you can list the values, although that list may be infinitely long. Whereas continuous random variables are random variables that can take on any value in an interval. The possible values of a continuous random variable are not restricted to any list. For example, decide whether each random variable is discrete or continuous. Y represents the number of bacteria in a petri dish in an experiment. Although this may be a very large number, the number of bacteria in a petri dish is discrete. They can be counted. R represents the average rainfall that Portland, Oregon receives per month. In this case, you can't count rainfall. You have to measure it somehow. The actual rainfall can fall anywhere within a given interval. Now, I suppose that we could cheat a little bit and round it off to a certain amount, like we could run it off to the nearest ½ inch or so, but that's not the true measurement of the amount of rainfall. X represents the number of defective routers in a shipment of 100. Since you could list the number of defective routers, there may be 0, there may be 1, there may be 2, there may be 3, and so forth, this would be a discrete random variable. So let's talk about the probability distribution for a discrete random variable. Let y denote an outcome in a discrete probability experiment. The probability that the random variable y takes on the value lowercase y is denoted as follows: P of capital Y equals y. Often we use the shortcut notation. We just use lowercase p of y. A probability distribution for the random variable y specifies the probability for each possible value y of the random variable. The probability distribution for a discrete random variable y can be represented by a formula, a table, or a graph. The probability distribution for a discrete random variable y is valid only if the following are true. Each probability for each outcome has to be between 0 and 1 inclusive. And if we sum up all of the possible values over all the possible values of y, those probabilities, then that sum must equal 1. For example, suppose that a fair coin is tossed twice. Let y be the number of heads that come up. We want to find the probability distribution of y. Here there are 4 equally likely outcomes to this probability experiment, and they're listed as follows. Event 1, or outcome 1, is that we toss a heads on the first, we have a heads on the first toss and a heads on the second toss. And then we have the other four possibilities here. Now we've looked at this in one of the previous lectures at how to come up with these different possibilities. We see there are three possible values for y. Remember, y represents the number of heads. There may be 0 heads in our two tosses, or we may have one of those two tosses as a head, or we may have two of those tosses are a head. So y can be 0, 1, or 2. Outcome E4 corresponds to y equals 0. That's where we have two tails. Outcomes to E2 and E3 correspond to y equal 1. There's exactly one head in each one of those outcomes. And outcome E1 corresponds to y equals 2 because there are two heads. And since we see that y equals 0 corresponds to one outcome out of 4 possible outcomes, the probability for y equals 0 is 1/4, or 0.25. To get one head, we can get that as either as a head on the first toss or a head on the second toss. There were two outcomes corresponding to that. So that means that the probability here would be 2 out of 4, or 1/2, which is 0.5. And the outcome corresponding to y equals 2, there's only one of them. That's where you have two heads, and that would be 1 out of 4 as your probability, or 0.25. So we can represent our probability distribution as a table, or we can represent that as a graph. Here we have a probability histogram. It's a little bit more common these days to see these probabilities for discrete events to be represented like this down here. We just have a single line. This represents a little bit more the discrete nature of the random variable that we're talking about. Expected value. So let y be a discrete random variable with probability function p of y. The expected value of y, which is denoted as e of y, is given as follows. Here the expected value is equal to the summation of y times p of y over all possible values of y. Now we can extend this definition a little bit. If g of y is a real valued function of the random variable y, then the expected value of g of y is given by the summation of g of y times p of y over all possible values of y. So let's look at an example. A study was done to see how many city blocks a fire engine could travel in a specified time interval. The study provided the following results. Let R be the random variable representing the number of blocks a fire engine would be able to travel in a specified time period. Find the expected number of blocks the fire engine can travel. Okay, so what we're going to do here is we're going to set up a probability distribution. We've got R, and because we're given the percentage of times here, we actually have P of R as well. These are just our probabilities, our proportions, which in turn are our probabilities. So let's copy this down. I'm going to just pause here and let me copy this down. Okay. So we've got our probability distribution here, and we want to find the expected value of R. So we want expected value of R, which we know is the summation of R times P of R over all possible values of R. So what that means is that we're going to take 21 times 0.05, that would be your first sum, and then the first term, and add that to 22 times 0.2, and add that to 23 times 0.3, and do this for all of these things. Now there are lots of ways that we could go about doing this. We could just do it manually and just kind of multiply these things out, maybe with the use of a calculator. Or we could use something like Excel. Now I've already typed this into Excel over here, so I've got my probability distribution written out. And remember what I need is I need for each value that's over here in column A to be multiplied by its corresponding value in column B. So I'm going to create a new column here. I'm going to say this is R times P. Okay, let's clean that up a little bit. All right. And so this is just going to be this cell right here, A2 times B2. And that gives me this one here. Okay, and I'm just going to copy that all the way down for the rest of these things. So what I've got here is I've got each of the products. And so I know that my expected value, E of R, is going to be, let me do that again, E of R is going to be just the sum of all of these things right here in column C. And so we see that our expected value is 23.4. Now, Excel actually has another command that will do all of this all together. So let me go in here and do this. Let's see. Okay. E of R. That command is sum product. So the sum product command takes two arrays, and all you're doing is those two arrays, you're going to find the products of the corresponding terms and then sum it all up, which is exactly what we're trying to do. So the sum product command, I'm just going to select all of the data here in column A, put in a comma, and then select all of the data here in column B, those corresponding values. And you can see that we get the same value. So either way you do this, Excel makes that a pretty easy calculation. Okay, so we have found the expected number of blocks that the fire engine can travel. There's a second part to this problem. Suppose that the number of homes, N, that the fire engine can serve is proportional to a circle of radius R, such that N is equal to 8 pi times R squared. We want to find the expected number of homes that the fire department can serve. Okay, so now what we're wanting is we've got a new variable, N, which is equal to 8 pi times R squared. And we want to find the expected value of N. So the expected value of N is the same thing as the expected value of 8 pi R squared. Now let's remember, if we go back here, that to find the expected value of a function of our random variable, we're just going to find the summation of that function times the associated probability. So what we want to do is we want to go over here and we're going to find the summation of 8 pi R squared times P of R over all possible values of R. And again, I think that we can use Excel to do this pretty easily. So I've already got my R values, and I've got my P of R values over here. Okay, so I'm going to create a column over here, and this will be 8 times pi times R squared. Okay, so that's just the title of my column right there. Okay, so what I want this to be is, this is equal to 8 times pi. Okay, now when I do this in Excel, I need to put an open and close parenthesis after pi. That's what tells Excel to put in the constant pi. Times R squared. So R squared is going to be the cell over here in column A, and I'm going to square that. Okay, and I'll just copy this all the way down. So this column is equal to N, which is 8 times pi times R squared. And so the expected value of this, according to our formula, is going to be 8 times pi times R squared times its probability, and then we sum all of those up. So I can do that either using the sum product, command that I showed just a moment ago, or I could create a new column just like I did here in column C and multiply each one of these times its probability and then sum those up. Either way I do that, I can find the expected value of N. And I think I'll just use the sum product formula. It's a little bit quicker. And so one array would just be these values here. And then I'm going to multiply those times my probabilities. Those are over here in column B. And I can see here that the expected value of the number of homes that the fire engine could serve is going to be this one right here, which is 13,800.39. So let's look at some properties of expectation. And here we're going to assume that C represents a constant and that G sub I of Y represents real valued functions. So the first property is that the expected value of a constant is going to be that constant itself. Well, that's not very tough to see. Another property is that the expected value of a constant times a function, in this case, you can just factor that constant outside of the expectation and just find the expectation of the function itself. And if we have the expected value of a function g1 of y plus g2 of y, we're trying to find the expectation of all of that, then we can break that into the expectation of the first function plus the expectation of the second function. Now, essentially what we are saying here is that expectation is a linear operator. In much the same way, if we think about things like finding derivatives, if I have a constant a times a function plus a constant b times a function, and I'm trying to find the derivative of all of that, then I don't really worry a whole lot about the a and the b. I just leave them where they are, and I apply the derivative to the function parts. And that's because differentiation is a linear operator. And we could do the same thing with integration. In this case, if I've got the expectation of a times some kind of a function of a random variable plus b times some kind of a function of a random variable, then what I can do is I can just leave the constants alone and find the expectation of the function parts. And that's what it means to be a linear operator. Okay, so then we can move on to the variance. The variance, denoted by sigma squared, is the expectation of y minus mu quantity squared. And that can be simplified into the expectation of y squared minus mu squared. And so let's see how this simplifies from this expectation to this simpler formula over here. So the variance of y is equal to the expectation of y minus mu quantity squared, which is equal to the expectation. Let's go ahead and multiply this out. So what we find is that we have the expectation of y squared minus 2 times mu times y plus mu squared. And because we know that expectation is a linear operator, this is the same thing as the expectation of y squared minus, okay, so mu here is just a constant, so this is going to be 2 mu times the expectation of y plus, and then the expectation of mu squared. Again, mu is a constant, so that's just going to be mu squared. And so we have an expression that looks something like this. But remember, the expectation of y, that's the mean itself. That is mu. And so what we have is we have the expectation of y squared minus 2 times mu times another mu, so that's a mu squared, plus mu squared, which ends up giving us the expectation of y squared minus mu squared, and that's a simpler formula. So let's reconsider the case where a fair coin is tossed twice, and y is the number of heads that appears. Here we want to find the variance of y, and we have our probability distribution given to us here. Okay, so I'm going to click over to Excel and just type these things in. So I have y, and I have, we've got y and we've got p of y. And so y can be 0, 1, or 2. And we found earlier that this is 0.25, 0.5, and 0.25. Okay, so let's clean this up just a little bit. Okay, so I'm going to start by finding mu. So mu, which is e of y. And I know that this is just the sum product. That's going to be each of the y values multiplied by each of their probabilities. So I select all of the values for y as my first array, and all of the values for p of y as my second array. And that gives me my mu. Okay, so to do the variance, I need to know what y squared is. So y squared is going to be whatever's over here in column A squared. And so now what we need is we need the expectation of y squared. So that's going to be the sum product of the y squares, that's what's in column C, that's my first array, times the probabilities. And so here I have the expectation of y squared. And so the sigma squared, which is your variance, is going to be, well, let's see, let's just type this in here. This is going to be the expectation of y squared minus mu squared. Let's remember from our formula, this is just the expectation of y squared minus mu squared. And so this will be this value, the expectation of y squared, minus this value squared. And so we've got our variance.